Hello everyone, welcome to lecture 34 of the online course Modern Display Technologies Flat Panel Display. Today's lecture will be on bistable, cholesteric, reflective displays and driving scheme. This is the part 1. In the next lecture we'll have the part 2. So here's the lecture outline. We'll first consider the cholesteric liquid crystal textures, talk about the planar, focal conic, fingerprint and the homeotropic ones. We'll discuss their optical properties towards Bragg reflection, color design and viewing angle. We'll then consider the grayscale versus via how we can get it via the multi-domain memory. Then we'll discuss multicolor and encapsulated cholesteric displays, transitions between cholesteric states, and we'll take a first look at the planar focal conic energy balance. With that, we will conclude this lecture and provide a bridge to the next lecture. So here we'll talk about the cholesteric liquid crystals. So the transition to a third distinct bistability mechanism will be discussed here. So this is the third bistable liquid crystal family. So the transition to a third distinct bistability mechanism will be discussed here. The cholesteric liquid crystals are basically chiral nematics with helical director structure, and their bistability and optical readout, that means reflection not transmission, are both qualitatively different from the ferroelectric and the pneumatic devices which have been covered in the previous lectures. So here let us define the pitch, that is P naught, carefully as the distance along the helical axis over which the director basically completes a full 2 pi twist. Okay. So this single parameter that sets the color of the light the material reflects, and that will be developed further in the next few slides. Now, depending on this orientation of the helical axis relative to the cell surface, 4 distinct textures are basically possible. So you can see here the planar, then this is called the focal conic, this is the fingerprint, and this is the homeotropic one. So in the planar texture, as you can see, the helical axis is basically perpendicular to the cell surface, okay, and this is the state that will carry the image information in a bistable cholesteric display. So what happens here, when the voltage is off, you will see the light is basically getting reflected, right? So you can also look into the other textures here. This one is called the focal conic. So you can see here the lights are basically getting focused over here. So here the helical axis is basically randomly oriented. So what happens, the light gets scattered in multiple domain. So light can come out this way or this way, right? Now if you look into the fingerprint axis, here what happens, here the helix axis basically lies in the cell plane. So that is basically at any intermediate field. So here the field is basically connected. So in these two cases the fields are not connected. And this is the homeotropic one. Here the helix is fully unbound at high field. Okay, so it is fully transparent, so the light is basically simply passing through without any scattering and all. Right. So here we'll basically introduce the visual signatures of each texture. Since microphotograph recognition is a practical skill, okay, so here you can basically see in a microphotograph the oily streak distribution lines, okay, can show for the planar texture and a malted multi-domain scattering pattern for the focal conic structure. Okay, that is the beauty of the micro photograph. So figure 2 basically shows this kind of micro photographs of the planar and the focal conic cholesteric structures. Okay, so The dark delineation lines are visible in this photograph of the planar texture, or you can call them as oily streaks. They basically mark where the cholesteric layers are locally bent. Okay. So, in the focal conic texture, the helical axis is basically oriented randomly throughout the cell. So, a multi-domain light scattering structure which is similar to the focal conic texture of smectic A. So, if you carefully look into this basically shows the microphotograph that shows the planar and the focal conic one. Now, neither of these states is naturally stable at zero field in an ordinary cell. So, true bistability basically requires surface stabilization, that means to make it homeotropic, or weak homogeneous alignment layers, or polymer sterilization by using a small amount of dispersed polymer. Okay. So, with either of this stabilization method, both the planar and the focal conic state become genuinely stable at zero field, and that basically is the foundation of the bistable cholesteric reflective displays. Okay. So, once again, if we stress on the key engineering point, okay, that we have seen in these 2 points, is that bistability of these textures is not automatic in a generic cholesteric cell. So, it must be deliberately engineered in. Either you can do it by surface stabilization or some sort of polymer stabilization, and this distinction recurs later, okay, when we will be discussing the weaving angle and the polymer stabilized black white variant. Okay. So, here we will see the fingerprint and homeotropic textures in more details. So, the fingerprint texture, as you can see here, appears at intermediate applied field. So, the field is applied here between the electrodes, and the helical axis basically lies parallel to the cell surface rather than perpendicular to it. Okay. So, there is no sharp boundary between the focal conic and the fingerprint texture shift. So, one can basically gradually shift into the other as the field basically increases. So, when you have sufficiently high field above a critical value that is developed in the part 2, means in the next lecture we will discuss that, the helical structure basically fully unwinds, okay, and the material basically reaches the homeotropic state that you are seeing here. That gives you a very transparent look of this cell, or the entire light gets transmitted and the director gets aligned with the field. So, what we see here is that neither fingerprint, because fingerprint is giving you scattered light and this is giving you transparent throughout. Okay. So, neither fingerprint nor homeotropic is used to store image information directly, because both are transparent states, because the material passes states that this material can pass through. Okay. And this is en route between 2 bistable, which is basically the planar or the focal conic states. Now, what are the optical properties involved here? So, in the planar structure, the refractive index oscillates periodically along the helical axis with a period of p0 by 2, and you can see that here n and minus n are basically physically equivalent, means the director position and the opposite of the director position both are basically physically same thing. So, the structure Bragg reflects light because it's a periodic structure, grating kind of structure. So, the reflection is basically like Bragg reflection, so we call it Bragg reflects light. Okay. That is basically centered at wavelength lambda naught, that is given as np naught, where n is the average refractive index. Okay. And the reflection bandwidth is delta n dot p naught, which is basically set directly by the material's birefringence, that is delta naught plays an important role in deciding the bandwidth. Now a cholesteric layer basically reflects only the circular polarization that matches with its own helical handedness, and it can transmit the opposite handedness, right? And if you talk about a single cholesteric layer, therefore alone it cannot exceed 50% of reflection when unpolarized light is falling on it, because only 50% of the light will be matching its own handedness, so that will be reflected, remaining will be transmitted. So what you can do, if you can stack a left-handed and a right-handed cholesteric layer together, then you can basically raise the reflection towards 100%. Okay, so each will basically reflect its own handedness. Okay, so we understood the formula of the reflected light here. So lambda naught will be the center wavelength of the reflection that will match the pitch of the helical axis, that is np naught, and the width will be basically delta lambda, that is the bandwidth is coming from delta n, that is the birefringence of the material times p naught. Now how do you define and design the reflected color? So a color absorption layer is basically coated in the bottom surface, and the display's overall reflected color is basically the sum of the cholesteric layer's reflection and the absorber's own color. So in the planar state, the cholesteric layer's own color basically adds to the absorber, and in the case of focal conic state, there only the absorber colors basically shows through. So you can take one example, say if you consider a black absorber plus a green reflecting cholesteric layer. So in that case the planar state will appear green, okay, and the focal conic state, okay, where you can directly see the absorber colors, it will appear black. Take another example where you have a blue absorber and a yellow reflecting color. Okay, so now the planar state always coming from, it is basically adding own color to that of the reflected. So it will basically add this blue and the yellow, and you will start seeing white as the reflected color. However, when you see for the focal conic state, okay, it is only the color of the absorber, that means it will appear blue. So why the choice of this absorber color is not arbitrary? Because it must be chosen relative to the cholesteric layer's reflective color, so that the two can combine additively, okay, since both are viewed by reflection. So you know your desired bright state appearance, so accordingly you should decide the color of the absorber, because when that color is adding up, it should basically give you the desired bright state appearance. Now let us discuss the viewing angle. Okay, so the viewing angle problem we'll see with the shifted wavelength formula. So a perfect single domain planar texture would show a color that visibly changes as the viewer's angle changes. So this is basically undesirable for any display that is meant to be viewed from many angles. Okay, so you consider light incident at an angle theta that shifts reflected wavelength to something like lambda now is a function of theta, and it is something like, say, n p naught cos theta. So at different angle you will start seeing different color. So in that case what will happen, your perfect planar texture will start showing angle dependent color. So you can see this particular figure, it is basically the polydomain imperfect planar texture, and this is what it is showing, that different angle is reflecting differently. Okay, so this is basically a micro photograph of the mottled polydomain planar texture, and this is a ray diagram that shows light from a single incident direction like this, okay, can get reflected of different domains into multiple outgoing direction. Okay, it can go this way or it can go this way, okay, like that. So what is the fix to this problem? So you have to deliberately introduce defects via dispersed polymers, or you can use weak alignment layers, and that will basically create a polydomain imperfect planar structure. And then it basically distributes each domain's helical axis over a range of angles around the cell normal, rather than making perfectly uniform. So under diffuse room light, each direction sees basically a mix of colors from many domains, giving a wide viewing angle displays appearance overall. Okay, so this is how it's gonna work. So under realistic room lighting, where you can assume the light is arriving from broad range of angles, there the mixture of colors reflected toward any of the viewing direction from many differently tilted domains basically average out. Okay, so that basically gives viewing angle independent appearance, okay, to the display. Now let us look into how we can get grayscale via multi-domain memory. This is becoming relevant because the bistable cholesteric texture is inherently multi-domain, where each domain is roughly 10 micron, which is invisible to the naked eye. So that makes the grayscale possible, unlike the most bistable nematic devices considered previously. Okay, so here each individual domain is itself strictly bistable, so it can be planar or focal conic, but nothing in between. So different domains can switch from planar to focal conic at different or slightly different voltages due to natural domain to domain variation. Okay, now a low applied voltage basically switches only a few domains to focal conic, so your high reflectance remains, because that is what happens in the planar regime. And when a high applied voltage is there, that only switches many domains to the focal conic, where the transmittance will pick up and your reflectance will drop. Okay, so that is how it is basically giving an analog grayscale reflectance, which is achieved from purely binary per domain memory, right? So each domain is only binary, either planar or focal conic, but the kind of multi-domain arrangement they have, that basically gives you this grayscale reflectance level. Okay, so the distinctive feature of bistable cholesteric displays that you see compared to ferroelectric and nematic devices here, okay, as compared to the previous two lectures, is that here the grayscale emerges naturally from the statistical distribution of the switching thresholds across many small individually binary domains, rather than requiring some special voltage time area partial switching trick that we discussed earlier. So that makes the cholesteric displays, okay, overcome the grayscale limitation that is shared by the SSFLC and the bistable nematics. Now here it develops the polymer stabilized black-white variant, only that was briefly introduced earlier in the grayscale slide, since it's a specific, practically important, reflective electronic paper style display. Okay, that's worth discussing, right? So in a regular polymer stabilized display with low polymer concentration, small domain tilt deviation, the planar texture's reflection spectrum is narrow, and you will see the reflected color to be pure. Now if the polymer concentration is increased, so that your n bar dot p naught, okay, so this is basically how the Bragg wavelength is calculated, right? That matches the wavelength of red light. The planar texture's reflection spectrum broadens dramatically, right? So you can actually see here in this particular figure 4, you see the two reflectance spectrum. Okay, so we are comparing P is the planar one, F is the focal conic. Okay, so here you can see reflectance versus wavelength, and the same can be seen over here. Okay, that is for the black and white cholesteric displays. Okay, so this is the regular one and this is the polymer stabilized one, right? So this spectrum plots basically show the regular polymer stabilized versus the black white polymer stabilized cholesteric displays, each showing separate curves for the planar and focal conic textures across the visible spectrum, as I mentioned. So here you can see that the spectrum basically dramatically broadened, okay, for the P curve, okay, in the black white variant, right? So what is happening here, the broadened spectrum basically makes the planar texture appears white rather than a single color. This is the polymer stabilized black white cholesteric display. So in this particular variant, okay, what happens to the focal conic, that also scatters more strongly rather than the regular polymer stabilized one. So you can see here this has also increased depending on the achievable black state. Now a single cholesteric layer reflects only one color, which is basically set up by its pitch. So if you want full colored, so what you can do, either you can use pixelation within one layer or you basically stack up multiple layers. So that is very important to achieve multiple color displays. Okay, so what is the single layer approach to this, that we'll be discussing now. So you can have alternating stripes of cholesteric liquid crystal with 3 different pitches. So each pitch will be reflecting blue, green and red, and they are separated by the polymer walls to prevent interstrip diffusion. So the first method could be you separate the mixtures. Okay, so you take 3 cholesteric liquid crystals with different pitches which are filled into empty pre-partitioned cells, and the other method can be photocolor tuning, right? Here a photosensitive chiral dopant can be added to the liquid crystal mixture that changes chirality and hence the pitch upon the UV exposure. So by masking and varying the exposure time, that will set different pitches region by region from a single starting mixture. So when you talk about the multicolor cholesteric design, since the pitch alone can set the single reflected color, so achieving full color will require especially either separating different pitches that we have seen here, okay, or you can think of stacking multiple single color layers together that will be seen here. So this is the multi-layer approach towards achieving multicolor display. So in this multicolor approach, what we do, you can stack 3 single layer cholesteric layers, each independently fabricated and then laminated together. So the best stacking order from bottom to top will be red, green and blue, and these are chosen to minimize cumulatively the scattering losses through this stack. And you can consider thin substrates which are ideally conductively coated on both sides, okay, that basically minimize the parallax between the 3 stacked color layers. However, there is a trade-off. So when you see the single layer, which is the pixelated displays, they are simpler to build, but you will see the reflection is less. However, when you consider this multi-layer or the stacked displays, they reflect more, but because of multi-layer they are basically thicker and they are harder to align. And this is the key design decision a display engineer must make between the 2 multicolor strategies. Now we will talk about the encapsulation in this cholesteric liquid crystal displays. Now encapsulation is a manufacturing oriented solution to a specific weakness of the pure unencapsulated cholesteric cell design that has been discussed so far. So here we'll see that mechanical squeezing can basically induce flow that disturbs the planar texture, erasing the stored image. Okay, so encapsulating the cholesteric liquid crystals into small droplets which are still larger, much larger than the pitch, will preserve the bistability while enabling flexible plastic substrate displays. So what are the methods? One can be phase separation method. You can mix the cholesteric liquid crystal with monomers or oligomers, then coat and laminate them between plastic substrate, and then finally polymerize. That way the liquid crystal phase basically separates out as droplets. Next comes the emulsification method, where you need to start the liquid crystal, water and a water soluble polymer at a high speed to form micron sized liquid crystal droplets, and then you coat and let the water evaporate. So what happens, these encapsulated cholesteric liquid crystals have much higher viscosity than the pure material that enables roll to roll coating, and crucially what happens, no longer flow. Okay, this flow problem is stopped because it no longer flows when squeezed, so that avoids the image erasing problem of the encapsulated cholesteric cells. So here we will actually provide a roadmap for the next lecture, part 2. You can see in this figure 5, this is basically the map of possible transitions among the 4 cholesteric states. So we have considered the transient planar state, and then you have the actual planar state here. You have the focal conic state, the fingerprint state, homeotropic state, and this is how they basically do the transition. So from fingerprint with high voltage you can go to this homeotropic state. With decreasing the voltage slowly you can come back to this state. From homeotropic, decreasing the voltage quickly, you can go to the transient planar state, and then if you relax at 0 voltage it will get to the planar state. Upon applying medium voltage you can come to the focal conic state, and similarly from this, if you directly apply medium voltage you can come here. From planar state with high voltage you can also come to the homeotropic state. Okay. Now why this transitions is important? So before designing a drive scheme, which will be discussed in the next lecture, we must first understand how the material moves between its 4 textures under applied field. So here we have seen that increasing field from planar drives the material towards the focal conic, then fingerprint, then homeotropic if the field goes further. So the pathway taken when the field is removed depends critically on how quickly it is removed. So slow removal basically favors one texture, something like here. From homeotropic, if you remove the field slowly you come back to this one, but if you do it quickly you will come to the planar state. Okay. So part 2 will examine in turn this planar focal conic transition, the fingerprint homeotropic transition, and the homeotropic planar transition. So these 3 transitions that matter most for the driving scheme design. So a first look, let us take at the planar focal conic energy balance. So the planar state has 0 elastic energy because there is no director deformation, and 0 electric energy because here the director everywhere is perpendicular to the field, right. So in the focal conic state it has positive elastic energy because of the bent cholesteric layers, but negative electric energy because the director locally is parallel to the field in some regions. So a sufficiently high field tips the energy balance towards focal conic, and this is why increasing the voltage basically drives the planar to focal conic switching. So in the next part, in the next lecture, we will examine how this transition physically appears via 2 distinct mechanisms, that is oily streaks and Helfrich deformation, and how the transitions threshold is kept high enough so that we can avoid display flicker. So here is a summary for this part, that we understood cholesteric liquid crystals store bistable information in the planar, that is basically a reflecting state, and a focal conic, that is an absorbing or scattering texture. Okay, so that basically made stable at zero field via surface or polymer stabilization. Reflected color can be defined by this formula, lambda naught equal np naught, and a polydomain imperfect planar texture gives a wide viewing angle. These displays are known for. This multi-domain structure additionally also enables genuine grayscale. So this capability was neither possible with SSFLC or bistable nematic LCDs, okay, that we have discussed earlier. So in the next part, we will talk about the detailed physics of how the material switches from the planar and focal conic and the conventional and the dynamic drive scheme, which are used to address a full passive matrix. So with that, we conclude this lecture. If you have got any query, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.